Okay, I just wanted to go through the setup for a conjugate heat transfer case, because that's something that I've done recently in OpenFoam, and so I thought it might be worth looking at. First of all, the meshing, and then secondly, the solver setup. So I've got some geometry here that I created. All of this has been created in Paraview. So I've got a box that's going to be my solid region. Inside of that, I've got a tube with an inlet and an outlet. So this is going to be the fluid flowing through the solid. Like I said, all of this was created in Paraview. I think this was done using a spline. So in Paraview, you can control left click, control left click, control left click. So yeah, you've got all of your spline points in a box here. You can add or remove spline points, and you can specify the exact location of them, which is really neat. And when you've got a spline, you can do lots with that. You can create surfaces by extruding it. You can even create 3D surfaces by having several splines together. I've covered that before. In this case, because it's just a tube, I went to use the tube filter. So you can create a tube. If you go over there, you can change the radius of the tube. Oop. And obviously you want to change the number of sides to 36, for example. So you can create a nice tube there. That's already triangulated, so you can extract surface, then you can save that as an STL. I'm not going to save it, but that's how this was done anyway. So you can create a tube, get rid of that. Now in this particular case, let's view it from above. There's a box, the solid region is the box. I'll just make that a bit opaque. I cheated a bit with this because I've got a box and I want the inlet and the outlet to show as separate surfaces to the box surface. And I think when I first did it, there was a bit of, don't know what you call it, bleed through of the box surface onto the inlet and the outlet surface. But I found that if I have the inlet surface just slightly inside the box surface, it seemed to, when it meshed okay. So there's a very small gap there, but you'll see when it actually finally meshes, and that worked okay. So yeah, so these are my 4 STL files. And where are they? They are in constant tri-surface. So that's the STL geometry. So what next? Yeah, there's also blockmesh. So if I go into the blockmesh dict, nothing very surprising about that. I've got these boundary patches. By default, I tend to use xmin, xmax, ymin, ymax, etc. But I think they're all set large enough to contain the all of the geometries. So in actual fact, the final mesh won't have any of the xmin, xmax stuff. It's just setting boundaries. So you specify your domain sizes here using those limits, and then you specify the mesh size 20 by 10 by 4. And so then when you run blockmesh, it does something. And if I opened that from the temp foam, then you can see that's my blockmesh. So that is, if I change the opacity on that, as you can see, that is big enough to contain all of the geometry. A bit too big, really. But I just did that in a bit of a hurry. So that's my blockmesh. And then I've got surface features. I've set up surface features for everything. So in surface features dict, I've just listed all of the geometry files there. So then I can run that. Surface features. And when surface features is run, you get these eMesh files in there. And then you get that extended feature mesh there. I'm not sure which one it actually uses, but it's all been created within the concept of directory. And then, last but not least, onto snappyHexMesh. If I open that up, I didn't use any layers in this test case, so I'll switch that to false. So you declare your geometry first of all, your STL geometry. I'll put a refinement box in just so that I can refine the whole region in one fell swoop. This mesh is quite small, so I think I've just got 100,000 there, but I could change that to 1 million. So yeah, the feature age refinement, I've set 2 on the box and 4 elsewhere, so that's doing the feature edges that's been created based on the eMesh. And the box level is 2, the tube inlet outlet set to 4. Now this is the interesting bit, because for conjugate you require meshing inside, not only the solid region but also the fluid region. So here you're not just specifying the level on the tube, you're also saying that it's going to have an internal face zone, and you're setting the face zone and cell zone to fluid, cell zone inside to inside. So that means hopefully it's going to mesh everything. And the refinement box region, that is set to 1. So that's just going to add 1 refinement. The location in mesh 0, 0, 0. Well, let's just get rid of that one. 0, 0, 0, source, point source. That is at 0, 0, 0. So we're specifying a location in the mesh to mesh the solid region. And so that's fine. But then because we've specified this face type internal and cell zone fluid, it's also going to mesh inside the tube. So save that. What else have we got here? Let's switch, get rid of all that. So then I can hopefully run that in Snappy. Excuse me. And that will create the mesh. Like I said, it's quite a small mesh, so it should do it fairly quickly. And when it's finished, we will, in theory, have a mesh with 2 mesh zones. So I'm not exactly sure how that works in the later versions of Paraview, but I tend to rather stubbornly just use Paraview 398 as often as I can because I just got used to it. And when I read the mesh into Paraview, we will see by default we'll just see the fluid zone. So we might have to, well, we'll see the whole mesh, but it might not display the zones differently unless we select read zones. So this is just running through doing the snapping to the surfaces and whatnot. So that'll take a few minutes to finish. So let's just have a quick look what we've got in here. For conjugate heat transfer, oh, that's finished already. Yeah, in conjugate heat transfer, we're actually going to have fluid and solid settings. So we've got different properties in the solid and the fluid, and the same thing goes for the system. In the solid and fluid regions, we've got separate solvers or separate solver files for each one of those. Now that that's finished, we've got a 1 and a 2. So let's read that in. Surface, right, that looks nice. So we've got, let's just get rid of all of the other stuff just to avoid any confusion. So now we've got the whole thing has been meshed inside and out. And on here, on the left here, we've got internal mesh. We've got all of these other boundaries which are, I think, going to be empty. And then we've got an inlet, an outlet, and a tube slave. So I'm not sure how much, if any, of that we'll actually be able to see. See the box. We're still encastellated. I'll just go to the latest one. That'll show the snapped mesh. So we've got the box. We've got some nice neat edges around there, so that looks good. If I switch the box off, I'm not sure if we will actually see tube or tube slave because that's internal. It's not going to show that, but we've got an inlet and an outlet. So yeah, I'm just going to switch on internal mesh again. And if I take a cut through that, in the Z plane, switch on the surfaces, switch off the triangulation and the plane. And so that is a cut through the mesh, and we can see the tube surface on there. So if I change that to VTK composite index, doesn't show it, so normals won't. If I go back up and then switch on read zones, it's complaining about some punctuation token. I don't know what that means. I'll go back to the slice. VTK composite index, and then we can see the two zones. VTK composite index. So what is that showing? That's showing value 1 on the solid, value 4 on the fluid. I'm not sure what happened to the other two values, 2 and 3, but at least that shows that we've got those those zones set up correctly as far as we know. So the next thing of interest, if I just have a quick look through the notes, It says in my notes, split mesh regions based on cell zones. Default region name is solid. So we've specified the tube as fluid, a fluid zone. And now we want to split the whole thing into two zones, two separate zones. And so if we do that, run that command. Oh, it says only one region doing nothing. That's interesting. Why has it done that? I have a feeling that is because with these directories here, it might be because of the value in control dict. That says start from 0. So what I'm going to do is I'm going to remove directory 1 and I'm going to move directory 2 to 0. So our mesh is now in 0. If I go into 0, I can see polymesh. If I go into there, I'm going to list the boundaries. So that's just showing box inlet and outlet at the moment. No mention of the tube. What else does it tell us? Cell zones, face zones. Cell zones, it thinks there's only one cell zone at the moment, but we know there's two, so that's why we need to split it. So look at the notes again. Right, so split mesh region based on cell zones. It's doing something now. It's done what we want it to do. So that, once we move that to 0, that has split and created the latest one in 1. So I can remove 0 and move 1 to 0. So this is just getting ready for this for when we start the solver. CD0, and we've got a fluid and a solid separately. And so the next thing to do is to set up the solver. We need to copy the boundary condition files into each one of these. And so if we actually try and load that into Paraview now, it won't really show us anything except the block mesh that's stored separately. So that's as far as we can go now with the meshing. The mesh is ready to go and ready to set up the case in ready to set up the solver conditions. So the meshing, as far as that's concerned, is finished now.